Right, today's topic is exponential growth and decay. This is a topic you may have seen in college algebra or pre-calculus, but here we're going to try to go a little bit deeper, especially in the beginning portion where when we explain to you where the exponential growth formula comes from. So typically in college algebra, you have seen this formula, A equals P times e to the RT, accumulated value equals principal invested times e to the power of r, the interest rate, and time being multiplied. So, but the question is, where does that formula come from? So that's one of the topics that we're going to take a look at today. So let's read this claim that we have on the screen. If a variable grows at a rate proportional to itself, then the growth is exponential. So typically when you put money in a bank, let's say that the interest rate is 5%, and money does grow at a rate proportional to itself. In other words, if you put a larger amount in a bank, then the interest you get will be higher, right? If you put $1,000,000, obviously at 3%, your interest will be higher there than if you put only $1,000 at 3%. So really, that's an example where the growth is occurring at a rate proportional to the existing amount, meaning the amount that you've invested. And it turns out that this idea is actually observed in many other phenomena, not just in money invested in a bank, but when bacteria grows, let's say, or when nuclear remains are decaying, or when people are getting, let's say, a raise in their company, they're getting a percentage of the existing amount, how much they're making. So this phenomena occurs in many different situations. So we're going to take a look at what is meant by this. A variable growing at a rate proportional to itself. How does that become an exponential growth? Let's take a look at what mathematics tells us about this. So let y of t represent the amount present at time t. Then this statement can be written as dy dt equals k times t. Now what does this mean? Dy dt represents the rate of growth or the rate of change of the quantity y if it is proportional to itself. So that means if it is proportional to the existing amount, that would be y. If dy dt equals k times y, then what we're saying is that the growth or the function will be an exponential function. That y is going to grow at a rate of exponential function. So how does this become? How does the left-hand side imply the right-hand side? Can we actually prove that? That's what we're going to take a look at next. So we're only assuming the left-hand side, and from there we're going to try to prove the right-hand side. And once again, the left-hand side is saying if the rate of change of a variable, growth or decay, is proportional to the existing amount. That's the only assumption we're making here, which is a very reasonable assumption. So if we start with that, what I'm going to do is I'm going to rewrite, first of all, the left-hand side. If dy dt equals k times y. Next, I'm going to try to put similar variables on the same side. Like I'm going to try to put the y's on the same side and multiply both sides by dt. So here I'm going to have dy over y equals k times dt. In differential equations, this method is called separation of variables. It's a very, very simple differential equation, and you can separate the variables. Now, to get rid of the derivatives, I'm going to integrate both sides. Now, think about the left-hand side. What is the integral of 1 over y dy? We've seen this in 1 over u du form. Same thing. Natural log, right? Natural log of absolute value of y equals, on the right-hand side, k is just a constant. It's the proportionality constant. If you integrate a constant with respect to the variable t, that is just k times t, right? Plus our integration constant c. Now let's go ahead and solve for y in this equation, because remember, ultimately we're trying to show that we will end up with an exponential function, that we need to solve for y. So to solve for y, to get rid of the ln, think about what you would do to get rid of the natural log. If you said I need to exponentiate both sides, like e to this power equals e to that power, then you were right because e to the ln, it cancels and you're left with y on the left hand side equals on the other side e to the kt plus c. I can further simplify the right hand side by writing e to the kt times e to the c. Because if you think backwards, going from here to here, if you had to combine these two expressions, you would have to add the powers, right? So that would give you the expression on the left-hand side. So that shows that we can't really split them like that. And now c is a constant, so e to the c will be yet another constant. I'm going to call that, let's say, capital C. So what I'm getting right now is I'm getting absolute value of y equals capital C times e to the kt. And what that means is y is equal to plus or minus the right-hand side. And I'm going to absorb it plus or minus c as another constant c. You know, you can pick another letter if you like, but I'm just going to just keep it my same old c, e to the kt. So basically what we're seeing here is that indeed with this basic assumption that the growth is proportional to the existing amount, we end up with the function being a constant times e to the kt. So this is really surprising. All of a sudden, out of nowhere, showed up this base e, and it's showing us indeed that with that assumption, our function will be an exponential function. And here, if you substitute t equals 0, what would you get on the right-hand side? C times e to the 0, and e to the 0 is 1, so you would get c. That means the meaning of the c is this is your initial amount present at the moment when time equals 0. So let's take a look at some examples. Again, the main thing here is how we have derived this formula, because that you could not have done in algebra. In algebra, we had to just give you a formula saying, okay, for all these questions, use this formula. But here, we're able to show you where the formula comes from. Okay, let's take a look at this simple example. $10,000 is invested at 7% compounded continuously. What is the accumulated value in 10 years? And when will the investment triple in value? So again, we can assume that money grows at a rate proportional to the existing amount. So we can assume that this formula, y of t equals c times e to the kt, is going to apply in this situation, especially when they say compounded continuously. And typically in this section, you can call y of t also the capital letter A. You can also write it like this: accumulated amount, or the amount present at any given time t, equals the initial amount times e to the kt. To answer part A, we want to find the accumulated value in 10 years. So use either of the notations. I'm going to use the first one. Accumulated value at 10 years equals constant, which is the initial amount, $10,000, times e to the kt. K is your growth rate, 0.07. T is the time, which is 10. So let's evaluate this. 10,000 times. Let's enter this into the calculator. So I need to have second ln, second natural log usually gives e to the power. Key, then you enter 0.07 times 10. Close your parentheses and press enter. You get 2.0138 roughly. 2.0138. And if we multiply it by 10,000, we just have to move the decimal basically 4 units to the left. And we're going to get 20,138 roughly. So in 10 years, we expect $10,000 to grow into $20,000. Part B, when will the investment triple in value? So we want to see when the final amount equals 3 times the original amount. So I'm going to set everything equal to 3c if the original amount invested was c times e to the kt. K is the growth constant, t is the unknown. Now at first it appears that there are two unknowns here, c and t, but if we divide both sides by c, that cancels out. So we really have only one unknown, that is t. And how do we solve for t in this equation? Since it appears in the exponent, we have to apply the inverse of exponential function, which is the logarithmic function. So I'm going to apply natural log to both sides. And then one of the properties of log says you can bring the power down. Ln e is 1. So to solve for t, we just have to divide both sides by 0.07. So t equals ln, or natural log of 3 divided by 0.07. And let's see what that turns out to be. Okay, I'm getting roughly 15.69. So let's just say 15.7 years is, or somewhere between 15th and the 16th year, you would expect this investment triple in value at 7% interest. And what is remarkable here is that it doesn't really matter how much you have invested. So you could invest a million and that will become 3 million, or 3 millions, or you could invest 1,000, that will become 3,000. So whatever the amount invested is, it will become 3 times itself in roughly 15.7 years at the given interest rate. Okay, let's take a look at another example. At what interest, compounded continuously, would $50,000 grow into $500,000 over 35 years? So we are given the final amount. I'm going to put it on the left-hand side. And again, when we hear continuous compounding and interest problems, we can assume exponential growth. And on the other side, the amount invested, which is 50,000, times e to the kt. K is unknown, that's the growth rate, and t is the time, that's 35. Again, how do we solve this equation for k? I would first want to isolate the exponential term by dividing both sides by 50,000. So if you divide 500,000 by 50,000, you'll get 10. And 50,000 over 50,000 here is just 1. So we get e to the 35k equals 10. And once again, to solve for a variable that appears in the exponent, you need to apply natural log to both sides. And let's bring the 35k down. Once again, ln e is 1. So to get k, we have to divide both sides by 35. So let's see what the growth constant is. So I'm going to enter ln of 10. Make sure you close your parentheses after that. And then division by 35. And I'm getting k equals 0.0658. But typically interest rate is given, I would say at most to the nearest tenths. So let's just say that this is roughly 0.066. In other words, 6.6% interest. Again, you can use more decimals if you choose to, but this would be sufficient for my purposes on the test. So 6.6% over 35 years will have an investment increase in tenfold. It will go from 50,000 to 500,000. Okay, let's do another example. I'd like to do this one, the half-life problem. It is given that the half-life of carbon-14 is 5,730 years. A piece of charcoal contains 15% of the original amount. How long ago was a tree burned to make the ancient charcoal? Okay, the definition of half-life is the time that it takes to go from let's say 1 gram to half a gram, or from any quantity to half of that quantity. So to end up with half a gram, that's the final amount. To start with 1 gram, it takes 5,730 years. What we don't know is K, because again, remember our formula for exponential growth and decay. So the final amount is a half, it's decaying. Initial amount is 1, time is 5,730, and K is the unknown. Let's solve for K to see what the decay constant is, and then we can answer the original question. So I will apply natural log to both sides. Once again, the right-hand side will simplify, just being 5,730K times ln E, which is 1. So to get K, we just have to divide both sides by 5730. So ln of 0.5, close the parentheses, divided by 5730 is, I'm getting something with e to the minus 4, so I'm going to have 0.3 zeros, and then 1, 2, 1, and it's negative. So it makes sense because there's a decay happening, and the decay constants are always going to be a negative value. Okay, now let's answer the original question. How long ago was the tree burned to make the ancient coal if we know that the charcoal contains 15% of the original amount? So the final amount is 0.15 of the original amount. So whatever that was, initial amount is C, final amount is 0.15 times C, e to the kt. K is negative 0.000121, and t is the unknown. Once again, you can cancel both sides. You can divide both sides by c rather, so the c's cancel. And to solve for t, I will apply natural log to both sides. And on the right-hand side, I have natural log of e to this power. And as we have seen in our past examples, the right-hand side will simplify as this. And to finish the problem, just divide both sides by the coefficient of t. And let's see what we're getting. Okay, what I got is 15,679 roughly. 15,679 years. So the coal was burned, the charcoal was burned more than 15,000 years ago. Now, if I had taken a few more decimals in my approximation, if instead of taking 1 to 1, if I had taken a few more decimals, such as 1 to, let's say, 0.968, the answer is slightly different. Then the answer comes out to be 15,682.8, so roughly 16,683. So there's a few years difference there, as you can see, depending on your rounding. So what I ask you to do is at least use 3 digits after the initial zeros, but the more you use, actually, the better. So if your answers are slightly different than the ones I listed in the back of the book, or the worksheets, don't worry too much about it. As long as you're consistent and you're using at least three significant figures, like like in this case, at least three decimals after the initial zeros, your answers are going to be okay. So this is a fine answer. This is a little bit more accurate, but either one is acceptable as far as I'm concerned. And finally, I want to show you guys another example, how you take some time to do it, and then I will display the answer. So take a moment to think about this problem. Please pause your video and then come back to it after you've solved it. And here's the answer for you to check. Once again, if we write in what is given, that will help us solve for K. And then they want to know the value of a Ford Mustang in the year 2000. That means 33 years after the initial amount. So that's why we're plugging 33 for our T variable. And that's why we're plugging 2300 as our initial amount here. So hopefully you got the correct answer on that one. Now go ahead and try the group activity problems if you can.